Okay, so we have now kind of finished our work on Sigma notation, at least introducing it and having a bit of a practice with it. It'll still be something you need to work on and practice quite a bit before you get fully used to it. But we're going to set aside that as a method for expressing series. And now we're going to come up with another method for expressing sequences. So previously, when we wanted to express a sequence, we just either wrote out the first few numbers and then did a dot dot dot, or we said the sequence is arithmetic and then gave two numbers in the sequence, or gave the first number and the difference, or we said the sequence was geometric and then gave two numbers again, for instance the first number and the ratio. But there are other ways of defining sequences. This is a common theme through mathematics, is you can invent your own definitions as long as they're useful. And one particularly useful way of expressing sequences is through something called recurrence relations. And recurrence relations are used when the sequence you're interested in has the property that an item in the sequence depends on what happened before. Sounds a little bit vague, but we'll see what I mean through some examples. And one particular example here is the Fibonacci sequence, which you may be familiar with. So just to get you started, you may be familiar with the sequence or not, but if you're not familiar, look at those numbers and see if you can describe in words what the pattern in the sequence is. See if you can spot it. And if you do know already what the sequence is and how it's generated, think of a way of writing it down mathematically. What would be a good mathematical definition for describing that sequence? So you can pause now. Okay, so the wordy definition is every item in the sequence is the sum of the previous two. So for instance, 8 is 5 plus 3, 21 is 13 plus 8. You get the idea. And additionally, that definition doesn't really make sense unless you tell me what the first two numbers are. So the first two numbers are just defined to be 1 and 1. And then from that, that's then sufficient to start generating the rest of the sequence. So this is an example of a sequence which is very well defined using a recurrence relation. It's this, and that's what I mean by the concept of every term in the sequence is defined by referring to previous terms in the sequence. And that is one example of that. It's saying take the previous two and add them together. But we can come up with all sorts of things. We could come up with, say, take the previous one and multiply it by 3, or take the previous 5 and add them together, right? There's all sorts of possibilities. All of those are recurrence relations. So let's look at recurrence relations. Let's define them a little bit more formally. So a few points to make. First of all, well, you can see it in the title there. A recurrence relation defines a sequence, right? So that is the purpose of a recurrence relation. It defines a sequence. A recurrence relation, it defines, it defines each term, so each number in the sequence, by referring to one or more of the previous terms. And in this case, now let's be a bit more specific. If you remember a sequence, we said a sequence is U1, U2, this isn't a bullet point, U1, U2, U3, and so on. And in general, we're talking about UN. So this is what a recurrence relation looks like. It says take UN and set it equal to some function which involves all of the previous ones. So some function of, it doesn't have to involve all of them, but it can if it wants to. So it can be a function of U1 and U2 and all the way up to anything before it. So the first one before it is UN minus 1, right? This thing here, this is a recurrence relation. Okay, that's our recurrence relation. And it's usually not going to be that complicated. You're not going to literally use every single term that occurred before. Technically you could, but usually you won't. An example could be something like UN equals 2 times UN minus 1. That's a nice simple recurrence relation. What does that one look like? It means take the previous number and double it. So if you say started with 1, then your sequence is going to be 1, 2, 3, 4, 5. What am I saying? It's going to be 1, 2, 4, 8, 16. It's just going to be a doubling sequence. You can also have constants in there as well. So another example could be something like, or any mixture. You could have UN equals, let's say UN minus 2 squared, and then add 1 to it. That's also a valid recurrence relation. What that one's saying is take the term 2 before, square it and add 1, right? Now what you'll have noticed is we haven't yet talked about what the first value is, right? And sometimes you need to define a few terms before you can get going with the recurrence relation. You need to tell me what I start with. The recurrence relation tells you how you get from one to the other, but it doesn't tell you what you start with. So that's the other key thing to a recurrence relation, is you also need the initial, I'll just call them the initial values, okay? And that will be something like U1 equals U2 equals, and how many of those you need to define depends on how far back in the sequence your recurrence relation is looking. If your recurrence relation is just UN equals 2 UN minus 1, you're only using the previous term. So you only need to tell me the first term, and then that'll be enough. That'll be enough as an initial value. This one, for instance, you're going to have to tell me the first 2 terms, because until you tell me the first 2, I can't look back 2 in the sequence. Does that make sense? So take the smallest one, in this case there is only one, UN minus 2, and look at the difference. What's the difference between n and n minus 2? It's 2, so that's how many initial values I want. So let's roll with this one actually. Let's use that, and let's give it some initial values, and let's say they are U1 equals 1 and U2 equals 2. Now everything in that green box is going to suddenly give me an infinite sequence. I don't know what it looks like yet, but all the information is there to give me that infinite sequence. And it is 1, 2, and then it says square. So in this case we've got U3, right? So U3 is going to be U1 squared plus 1. So it's going to be 2. And then what do we get for U4? Square U2 and add 1, we get 5. And then U5, square U3 and add 1, we get 5. And then U6 is going to be square and add 1, and so on. Okay, so it's a bit of an interesting pattern. So recurrence relations can define all sorts of weird sequences. They don't need to be arithmetic or geometric. In the examples we look at, it may be the case that they actually are. But what I've tried to give you here is more of a general overview of recurrence relations. It probably doesn't need to be this general when you actually start applying it to the questions we'll look at. You're not going to have a function of multiple, or at least many u's. The most you'll get is maybe 2. You're not going to have un minus 1 and un minus 2 and un minus 3 and so on. Okay, and to just end with, let's actually answer the starter question, right? What is the mathematical way of describing the Fibonacci sequence? So for Fibonacci, we would define it as follows. Our initial condition, or our initial values, is u1 equals 1, u2 equals 1, un is equal to un minus 1 plus un minus 2. Okay, this bit here, that's the recurrence relationship, and this bit here is the initial values. Okay, and because the Fibonacci sequence looks back 2 values into the past, you have to specify 2 initial values to start with, otherwise it's not going to work. Okay, and then one other thing I want to point out before we look at some examples, which will hopefully make things clear, is that this concept of shifting the index in a recurrence relation. And this is more about trying to point out that there's multiple ways of expressing exactly the same thing, and to hopefully avoid a potential bit of confusion. So you remember with, well, let's write it again. The Fibonacci sequence, we said it was this, right? And we said it was un equals un minus 1 plus un minus 2. Now, what you can do in a recurrence relation, you could say to yourself, well, actually, I want to define the Fibonacci sequence a different way. What if I said un plus 1, right, is equal to un plus un minus 1. So it's like saying the one in front is equal to the one I'm at plus the one behind me. That makes exactly the same sense, right? Or the same amount of sense. You could even say the one that's 2 ahead is equal to the one that's 1 ahead plus the one I'm currently on, right? All 3 of these are exactly the same recurrence relation. I'm just writing recurrence relation as rec-rel. It's the same recurrence relation. And the way you can tell if 2 recurrence relations are the same is if by a single substitution of the index, n in this case, you can turn from one to the other. So for instance, to go from this one to here, all you have to do is say n equals n plus 1. Or that's sorry, that's a bad way of writing it, because that implies n is some non-existent number. Let's say n goes to n plus 1. And you can see if you did that in all cases, then you transform the subscript here to all the subscripts here. Or likewise from un to un plus 2, you're adding 2 each time, and it works here as well, right? n minus 1, add 2, you get n plus 1. n minus 2, add 2, you get un. So you may freely do this, and all 3 of those are correct. They're all representing the same Fibonacci sequence recurrence relation. So just keep that in mind. You may sometimes see a recurrence relation defined as un equals. It may sometimes be un plus 1 equals, but it doesn't really matter. There's no reason why you can't do one and can do the other. You can do either one. They're both acceptable. Okay, let's look at some examples. So starting off easy, we just want to learn how to use recurrence relations, is how to read them. Find the first 4 terms of the following sequences. So part A, here we're given the recurrence relationship, And then it's just subtly separated by a comma here. We've got this part here, which is the initial value, the initial val. Okay. Find the first four terms. So I'm going to write the initial value first. This is U1. And I'm going to be finding the first four terms. So I want U2, U3, and U4. The recurrence relation says UN plus 1 equals UN plus 4. So I read that as the one in front is equal to where I'm at plus 4. So if I'm at 7, then the one in front is 7 plus 4. So we get 11. Make sense? Another way you can read it is as follows. The recurrence relation allows you to stick in any value for n and it returns a true statement. So let's look at the recurrence relation in more detail. Again, it looks like this, right? We have to be careful that n plus 1 is a subscript, that plus 4 is not. I can plug in any n I want and I get a true statement. So if I want to know what if I want to know what u3 is, let's put in n2 or n equals 2. Then we'll get u3, right, for n equals 2. And that then equals u2, because n is 2, plus 4. And that is a true statement. So again, it's telling me what I already knew. u3 is going to be u2 plus 4. And then we can see the pattern, right? So you've got two ways of interpreting the recurrence relationship. They're both equivalent. One way is to use this sort of mental model of thinking about the one I'm on, the one ahead, the one behind me, and reading it that way. The other way is to just put values for n in, and you can choose, and you can try n equals 1, try n equals 2, and try n equals 3. Each time you substitute a value for n, you will get a true statement, and that true statement will be a relationship between various terms in the sequence, and you can then apply that relationship to get values that you don't already know. Okay, let's look at B. Oh, it's almost exactly the same. That's a bit too easy, isn't it? So it's exactly the same rule, but you're starting with 5 instead. U1 is 5, and then you add 4 to the previous to get the next one. So we get 9, we get 13, and we get, wait, yeah, sorry, moment of hesitation there, couldn't add my 4s. 5, 9, 13, 17, that's it. Okay, and then let's look at our final example before I give you some to try out. So we've got a sequence, A1, A2, A3. Here, instead of using the default U letter, the letter U, they're just using A instead for no particular reason, but that's fine. And it's defined as follows. The initial A1 is P, where P is just some constant, some number, I don't know what it is. And an plus 1 is equal to an squared minus 1. And that's true for n greater than or equal to 1. Okay. So, and p is less than 0. So we're going to show that a3 equals p to the 4 minus 2p squared. Okay, that's going to be our part A. So to do this, let's do the following. We're going to write a3 equals, and then we're going to use the recurrence relation and see what we get. A3, if I choose n equals 2, will give me the left side of this recurrence relationship. So when n equals 2, I get A3 here. So then I'm going to also see what happens to the right hand side when I put in n equals 2. I get A2 squared minus 1. So that recurrence relationship has given me the following information, right? And then I think, okay, do I know what A2 is? No, it's not given as an initial condition. So I'm going to kind of repeat this process. Let me put a bracket where A2 is. And now we're going to have to see what A2 is. So let's go back to the recurrence relationship here. When n is 1, I get A2 on the left. And when n is 1 on the right, I get A1 squared minus 1. Okay, so now I have that A3 is equal to A1 squared minus 1 all squared minus 1. And I know what A1 is, right? It's P. So now we've used the recurrence relationship enough times that I can now put in the initial values. And we get P squared minus 1 all squared minus 1. Let's multiply that out. We get P to the 4 plus 1 minus 2P squared. And I've still got that minus 1 outside. The plus and minus 1 cancel. I get P to the 4 minus 2P squared. And that's what I wanted. Okay. All right, next, given that A2 equals 0, find the value of P. Okay. Let's see. Well, hang on. So the easiest way to do this is to say, well, this thing here, we just worked out was A3, but A3 is also equal to this, A2 squared minus 1. And we were just told that A2 is 0. So this is 0 here, right? A2 squared. So in other words, this thing here is equal to minus 1. So we've got P to the 4 minus 2P squared equals minus 1. Or as a quadratic, it's plus 1 and equals 0. Right, okay, so we now need to find the value P. Right, okay. You know what? There was actually a faster way to do this. But we can quickly finish this, and well, we'll do this, and I'll show you what we could have done. This P to the 4 minus 2P squared plus 1. This actually, if you spot it, and this might be a bit hard to spot, is actually just P squared minus 1 squared. However, you wouldn't have needed to spot that because actually I was a bit silly in comparing this one here to here, because what I could have done is compared that one to this part here, right? In other words, this thing is A2 squared, or in other words, A2 is P squared minus 1, and P squared minus 1 is 0. We could have done it that way. But it's fine, we've done it this way. We still get the same result. P squared minus 1 is 0, which implies P is equal to plus or minus 1. But we were told P is less than 0. So therefore, P is minus 1. Okay. Right, so then part C. We're going to find the sum from the sum of the first 200 values, effectively from 1 to 200 of this sequence. So perhaps, let's see, what's the best thing to do here? I think, remember, when in doubt, always just work out the first few terms of the sequence, see what you get, and see if you can recognize it as something meaningful. So let's just do the first few values of the sequence. We've already got A1 is P, which is minus 1. So our sequence or our series starts as minus 1, and then we can use the rule, right? So you square it and you take away 1, and that gives you the next one. So if I square minus 1, I get 1, and I take away 1, I get 0. Square it, take away 1, that gives me minus 1. Oh, okay, so in that case we're going to get a cycle, right? Because minus 1 squared minus 1 gives you 0. 0 squared minus 1 gives you -1. So we're going to keep repeating. 0, -1, 0, and so on. This is an interesting question. So we're going to find that sum, effectively. Let's put the -1s in brackets so this looks a bit more proper. And we're going to do that 200 times. So this is where series get interesting, because you just have to you have to think about what you're actually working with. You can't just necessarily blindly plug in numbers into formulas. If I have 200 of this happening, right? So this is the first, this is the second, this is the third, fourth, fifth, sixth, seventh, and so on. What do I actually have in total? I'm going to have 100 -1s, and I'm going to have 100 zeros, right? So if I add that all up, I'll just have -100, and that's the answer, -100. Okay. And then finally, write down the value of A199. So 199 is obviously quite a large number. You could plug in your recurrence relationship 199 times, but what would be more sensible is for you to observe the pattern that we've discovered here. So whenever the index is even, we have 0, and whenever the index is odd, we get -1. So in this case, 199 is an odd number. It's an odd index, so it's just -1. Okay, and that's it. So hopefully that's given you some idea of how we work with recurrence relations, the kinds of interesting patterns that they can give us. Notice that in this case, that specific series we had, it's not arithmetic, because you're not adding the same number each time, and it's not geometric either. So this is, I guess, our entry now into working with series where it's neither arithmetic or geometric. So that's precisely why we couldn't use a formula in this case. But luckily, we were able to recognize the pattern and find an answer. Okay, so first slide of questions. See how you do. For this first one, number 3, I just want to make it clear what you've been given is not a recurrence relation, right? I know it looks similar because you've got a UN and an equals, but this is just your bog standard sequence definition, right? It's not UN in terms of n-1. For instance, 3a, it just says UN is 2n-1. It means you put in an n and it gives you the value of the sequence of the term at that specific n value. So it's not actually a recurrence relation. A recurrence relation is when it's UN or UN plus 1 in terms of UN minus 1 or UN minus 2 or something like this. So what they say here is write down the first 4 terms, or otherwise find the recurrence formula. I would suggest find the first 4 terms or 5 terms or whatever. So for instance, for 3a, put n equals 1, n equals 2, n equals 3, n equals 4. See what numbers you get, and then see if you can write that in a recurrence relation form. Okay, so the recurrence relation form requires the relation itself and the initial values. Make sure you also specify the initial values. If you don't specify initial values, your recurrence relation is useless. It doesn't give you the sequence. Okay, so I would recommend giving all of part 3 a go, because they're all a little bit different really. And then you can go on to number 4. So pause the video now, give those a go. And finally, we've got one here. So this is an interesting recurrence relation we've got. It makes use of the previous term twice. Just one initial condition or one initial value. So see if you can find x3. We've done something similar to that in a previous example. find the value of P given the x3 value, and then can you find the x4 value? So 4 marker, give it a go. Pause the video now.